Our next speaker will be Chase Cooper, and as the slides get pulled up, he will be speaking to us about extreme forward scattering observed in disk-averaged near-infrared phase curves of Titan. Go ahead and take it away when you're ready.
Hello, hello. Sounds good to me. All right. Well, hello everyone. I am Chase Cooper. I am an undergraduate astronomy student here at the University of Arizona. For the last 18 months or so, I've been working with Dr. Tyler Robinson over at LPL on this project about near infrared phase curves of Titan. Just to make sure that everyone's on the same page, a phase curve is basically what you get when you plot the brightness or the albedo or some other radiometric quantity of a planetary object like Titan against the phase angle that you measure that brightness at. And the phase angle here in alpha is just the angle between the star, the object you're looking at, and the observer. So when you want to construct a phase curve of an object like Titan, Earth observations, as wonderful as they are, just don't provide the phase coverage that you need. From Earth, you can only ever really view Titan at phase angles of 6.5 degrees or less. So we make use of observations from the Cassini probe. Cassini was in orbit around Saturn from 2004 to 2007. And during that time, it made over 100 flybys of Titan. So it had the opportunity to observe Titan at a wide variety of phase angles, anywhere from 2 degrees all the way up to 165 degrees of phase. The other great thing about Cassini is that its visual and infrared mapping spectrometer is the instrument that we take the observations from, also made simultaneous measurements at wavelengths from 0.9 micrometers all the way up to 5.1 micrometers. So we also had great spectral resolution in our data. So the first thing that we did is we developed a pipeline basically just to calibrate the images and to sort out all the images that don't have the complete body of Titan in their field of view. The next thing we did is basically integrating over the disk of Titan, and this is part of the process. I'm not going to go into it in too great of detail here, but we integrate over the disk of Titan to get a disk averaged value for the brightness of Titan. And we do that because we want the observations to simulate what an exoplanet would look like. Current observatories can't directly image or let alone spatially resolve terrestrial exoplanets around other stars. So with the data from that pipeline, we produced we produced a comprehensive set of phase curves of Titan in these near infrared wavelengths, which is what's on screen here. On the x-axis is phase angle, and on the y-axis is brightness. Some works will write this brightness as I on F. We use AG phi, or the geometric albedo, times the planetary phase function. It's all the same. And a really interesting thing that we'll talk about a little bit more in a second is that Titan is actually brighter at these high phase angles than they are at low phase angles. Another thing that we can do is we can take observations of Titan that are at very small phase angles, and we can use that to approximate the geometric albedo of Titan. So in this plot here, wavelength is on the x-axis, that approximate geometric albedo is on the y-axis. We also, our values are in red. We also included data from work by Eric Karkoschka in the 90s, who did Earth-based imaging of Titan. And it's in decent good agreement. There are reasons why there is a big discrepancy around here, just due to saturation, but there's also recent work using JWST data of Titan that is also in pretty good agreement with this spectrum. A couple of notable features is you see these spikes anywhere from 1 to 2 microns, and then again at 2.8 and 5. Those are indicative of wavelengths that aren't absorbed by Titan's atmosphere. The gaps in between are just due to atmospheric methane absorption. There is also a feature at 3.3 microns. This turns out to be stimulated emission by methane on the day side of Titan. And it's pretty cool to see that you could see this in disk average observations. And then there's another feature at 4.5, which we don't actually think is real. So we're going to ignore that for now. So what do we make of this? Notably, Titan appears brighter when you look at it when it's backlit versus when you look at it at full phase. And this is weird. When you're observing a planetary object, you expect it, when you go from low phase to high phase, you're observing less and less of the illuminated fraction of that object. So you would naturally expect it to be dimmer. Titan doesn't do that. The reason for that is that Titan's atmosphere is full of haze particles that are basically scattering the sunlight. The haze particles are about the same size as the wavelength of light, and so that places it in the Mie regime. I have to be careful to say it's not Mie scattering because it's not. But when you have particles about the same size as the wavelength of light they're scattering, you get this really strong forward scattering effect. And so what's going on here is that the hazes on Titan are scattering the sunlight around the solid body back towards the observer. And this was observed before in visible light. I'll just show this for reference. This was observed before in visible light. There's a paper by Antonio Garcia Munoz et al. Back in 2017 that looked into this. However, we found that at near infrared wavelengths, specifically at wavelengths with methane absorption, this effect is really strong, like on the order of, so strong that Titan appears at some wavelengths over 10 times brighter at these high phase angles than they do at low phase angles. The other thing we found is that in the phase curves at these atmospheric window wavelengths, you get this large variability at small phase angles. Because this was at atmospheric window wavelengths, we assumed that this was some sort of surface or lower atmosphere feature. And we believe that at least in part it was. And because in our images, you can actually see clouds on Titan. So what's this good for? Phase curves are a really good product for categorizing or for characterizing not just solar system objects, but also exoplanets. Future observatories like the Habitable Worlds Observatory will be able to directly image terrestrial exoplanets around other stars. And they will take multiple images as they orbit their star, allowing us to construct partial phase curves of those exoplanets. Understanding Titan's phase curve is very important because we can understand how hazy atmospheres will manifest in these phase curves of other planets. And it also helps us disambiguate from other phenomena that create similar effects. In particular, we looked at glint on Earth, ocean glint, which is sunlight bouncing off of a relatively smooth ocean. It creates a very similar brightness at high phase angles. So how do you disambiguate haze from glint? We found that the best answer was probably their wavelength dependencies. Glint is predicted to get stronger at redder wavelengths, and also you would only see it at wavelengths that are transparent to the atmosphere. Whereas with hazes, you actually see quite the opposite. The forward scattering due to hazes is especially strong at wavelengths where you would expect atmospheric absorption. So I will go ahead and throw up the summaries of what I just said. And then if you're interested in the paper is accepted to be published, but it's not published yet, so it's up on arXiv now. And I'd be more than happy to take any questions.
Questions for our speaker?
Thanks for your talk, Johanna Teskey, Carnegie Science. So with a lot of small exoplanets, or not a lot, but the ones we have, we're seeing some evidence of hazes that have different properties than the hazes on Titan. And so I'm wondering if you can just comment on kind of extending your work to maybe different assumptions about the haze composition or particle sizes.
Yeah, absolutely. So this sort of the wavelengths at which you see this kind of effect is also dependent on the size of the haze particles. So for sure, if you were able to, I guess, construct phase curves of these hazy exoplanets, they will have different wavelength ranges where at their strongest, and that will infer the size of the haze particles. There is probably also something that could be done with polarimetry. I don't know how keen people are on using polarimetry on future observatories, but they also can tell you information about whether or not the particles are spherical, or if they're like, in the case of Titan, they're aggregate particles. So they're basically just a bunch of balls stuck together.
I think there was an SCDD for Huo on polarimetry. Other questions? All right, so if there's no other questions, let's thank our speaker.